Hello, organic chemistry students. In our last video, we were focused on carbocyclic aromatic rings. And what I mean by carbocyclic is that the rings were comprised solely of carbon. In this video, I want to introduce you to heterocyclic aromatic rings. What do I mean when I say heterocyclic? Well, you may recall that a heteroatom is any atom that is not carbon or hydrogen. So a heterocyclic molecule is a cyclic compound that has some atom other than carbon as a part of the ring. And these four molecules that you're seeing here, pyridine, pyrrole, furan, and thiophene, are heterocyclic aromatic compounds. So they have a heteroatom in the ring, and they are also aromatic. Let's have a look at these compounds and see how and why they're aromatic. Let's start with pyridine. Well, you may recall our rules for aromaticity, and one of the rules said that all of the atoms in the ring had to be sp2 hybridized. If you look at pyridine, you can obviously see that they are. The molecule has to be planar. If all of the atoms are sp2 hybridized, then indeed this molecule is planar. You also need to have the right number of pi electrons. So let's count our electrons. I have 3 pi bonds, or 6 pi electrons, and that fits our formula, Huckel's rule, 4n plus 2. In this ring, we have all of the criteria for aromaticity satisfied. I do want to point out to you, though, that this lone pair of electrons resides in an sp2 orbital, and it is not part of the aromatic pi system. If we consider the molecular orbital picture, you can see that we have our 6 electrons, all residing in unhybridized p orbitals, and this lone pair of electrons is located in an sp2 orbital and is not part of the aromatic pi system. If we look at the electron density map, we can see that the electron density from that lone pair of electrons is highly localized. It is not delocalized into the ring. Let's consider a couple of other molecules, pyrrole and furan. If I look at pyrrole, you can see that all of the carbons in the ring appear to be sp2 hybridized. The way that I've drawn the nitrogen, it appears to be sp3 hybridized. But let's have a closer look. We have 2 electron pairs, or 4 pi electrons. That even number of electron pairs does not fit our criteria for aromaticity. In order for pyrrole to be aromatic, it's got to use that lone pair of electrons on the nitrogen as part of the aromatic pi system. So the lone pair on the nitrogen is part of the pi system. You'll see that that's true also for furan. The nitrogen and the oxygen are sp2 hybridized. Even though the way that I've drawn these molecules, the heteroatoms do not appear to be sp2 hybridized, remember in the example of the cyclopentadienyl anion, we said that if sp2 hybridization could result in aromaticity, then the atom will indeed be sp2 hybridized. If we have a look at our molecular orbital picture, you can see that we have 1 p orbital on each of 4 carbon atoms, contributing 4 pi electrons, and we have 1 p orbital on the nitrogen that contains 2 pi electrons, or that lone pair of electrons. So let's go ahead and count them. We have 1, 2, 3, 4, 5, and 6 electrons as part of our aromatic pi system. And that does satisfy Huckel's rule, 4n plus 2 pi electrons, where n is equal to 1. If we look a little closer at furan, we have 1, 2 double bonds, or an even number of pi electron pairs. This means that furan will have to use one of its lone pairs of electrons from the oxygen as part of the aromatic pi system. The second lone pair is located in an sp2 hybridized orbital and is not part of the pi system. This is what our molecular orbital picture looks like. Each carbon atom is sp2 hybridized and contributes 1 electron. The oxygen is also sp2 hybridized, but it contributes 2 electrons to the aromatic pi system. So we have 1, 2, 3, 4, 5, and 6 pi electrons. We can draw a number of resonance contributors for parole by pushing that lone pair of electrons into the five-membered ring. This causes a separation of charge, with negative charge distributed across the carbons and a positive charge on nitrogen in 4 out of our 5 resonance contributors. So this lone pair of electrons gets pushed into the aromatic ring, and you can see from our electron density map that we have a lot of positive charge located on that nitrogen, and we have a lot of electron density in the ring. The pKa of protonated parole, meaning this lone pair of electrons grabs onto a proton, is minus 3.8. That is a very, very strong acid. In other words, we can say that parole does not want to be protonated. It does not want to accept a proton. Parole would rather use that lone pair of electrons on the nitrogen as part of the aromatic pi system in order to gain that extra stability from aromaticity, rather than using that lone pair of electrons to grab onto a proton, because that would mean that parole would lose its aromatic character. We can draw similar resonance contributors for furan by taking that lone pair of electrons and pushing it into the ring. This causes a separation of charge, distributing the negative charge onto the carbons and a positive charge on the oxygen in 4 out of the 5 resonance contributors. We can see from the electron density map that we still do have significant electron density on that oxygen atom. That's because it still has a lone pair of electrons that it is not using as part of the aromatic system. And we do have some negative charge distributed into the ring. Here are some bicyclic, heterocyclic aromatic rings. So these compounds are aromatic. I want you to take a minute and look at these molecules and decide which of the lone pairs of electrons on the nitrogens are being used as part of the pi system and which are not. So go ahead and pause the video, and I'll tell you the answers when you come back. Alright, let's see how you did. Let's count up our electrons in quinoline. We've got 5 pairs of pi electrons, so we have an odd number of pi electron pairs. What this means is that the nitrogen does not need to use that lone pair of electrons as part of the aromatic system, because we already have the right number of pi electron pairs without it. Quinoline pretty much looks like a benzene ring fused to a pyridine ring, very similar to pyridine. Let's have a look now at indole. Here I have 1, 2, 3, 4 pairs of pi electrons. Well, that's an even number of pair electrons. That does not fit our criteria for aromaticity. So in order for indole to be aromatic, it has to use that lone pair of electrons on the nitrogen as part of the aromatic pi system. What about purine? I've got 1, 2, 3, 4 double bonds, or 4 pairs of pi electrons. That number isn't right. It doesn't fit. I need to add an additional pair of electrons in order to make purine aromatic. You can see that I have 4 lone pairs of electrons. Which lone pair am I going to use? Well, I'm going to use this one right here, because when this nitrogen is sp2 hybridized, this lone pair of electrons can exist in an unhybridized p orbital. The other lone pairs of electrons on the other nitrogens are in sp2 orbitals.